In this lecture, we'll look in a little more detail at the radial velocity method for detecting exoplanets. Remember, the radial velocity method is a measurement of the reflex motion of stars as a way of detecting exoplanets that cannot be seen directly. The observed light is periodically red and then blue shifted, recurring each orbit. The data can be added together because the orbit repeats, and so the data can be gathered red and then blue shift, red and then blue shift over many orbits. And that also allows us to push the precision of the technique and detect lower and lower mass planets. This periodic Doppler shift is measured by taking a spectrum of the star and taking a spectrum over a period of time, over and over again, and carefully comparing the spectra. So it requires an instrumental method that establishes a very careful and precise and stable zero point for the spectroscopy wavelength to allow us to detect its variation by relatively small fractional amounts. The magnitude of the Doppler shift indicates the speed of the reflex motion or the radial velocity of the star. We make a spectrum with a spectrograph. That's a key instrument of astronomy dating back to Fraunhofer, who first made spectral measurements of the sun in the year 1800. So spectroscopy has been a key to astronomy ever since 1800, for over 2 centuries. Late in the 19th century, spectroscopy was used to see elements in the universe and what the composition of stars were. In fact, helium was first discovered in space in stellar spectra before it was ever discovered on the Earth, raising the question of whether it was some strange element unknown on the Earth. In the early to mid-20th century, careful observations of stars showed that the stars were made of primarily hydrogen and helium. And then even more careful observations showed what the relative abundance of all the elements in the periodic table were in solar system material or in the atmospheres of stars. So spectroscopy has been a key method for learning about the universe. In this case, we're using spectroscopy in a very precise way to look at very small spectral shifts over time. The way this is done is by using the absorption lines in a star's spectrum. In a star like the Sun, radiation is produced in the stellar core, and the cooler gas in the outer atmosphere of the star imprints absorption lines, which are absorption features keyed to the particular energy transitions of the atoms that the star is made of. And so in this toy spectrum, you can see the smooth continuous spectrum caused by the temperature of the star has overlaid on it dark notches or absorption, and that pattern of absorption corresponds to the spectral lines emitted primarily from hydrogen and helium, the 2 elements of which most stars are made. These black lines are called absorption lines, and that pattern is like a fingerprint. The pattern of absorption lines is unique to each element or to each combination of elements in the periodic table. These spectra can be characterized by laboratories on the Earth. So as a reference point for what we see out in the universe, out in space, you can have a gas in a cell at low density, excited by energy or radiation, which does the same thing. It emits emission lines or absorption lines with the characteristic pattern corresponding to the chemical element involved. And so that's our zero point, because the gas in the lab or in the telescope control room is not moving, and then we compare it to what's happening out in space. So the absorption lines in stellar spectra are serving essentially as markers of wavelengths. And if the lines are not at the same wavelengths as they appear in the lab for that same element, then we know the source emitting the light must be experiencing some kind of motion. Now, it helps in the detection of exoplanets that these absorption lines are extremely narrow, allowing us to define their mean wavelengths at rest extremely accurately, tiny fractions of a percent. And that gives us corresponding precision in measuring the motion of a celestial object. So by monitoring the motion of a star over time, we observe the periodic Doppler shift as the absorption lines appear to be red-shifted and blue-shifted. And this cartoon shows what's happening. There's the orbit of the planet around the star, about a common center of gravity, the reflex motion, and that star wobble, while invisible on the plane of the sky, manifests in terms of a spectroscopic shift. And so the lines, the absorption lines of any particular element in the outer envelope of the star will shift red and blue with a sinusoidal variation in wavelength over time corresponding to the orbit, and each orbit it repeats. So we define this as the radial velocity of the star, which is the component of the star's motion towards and away from the observer, or us. There's also a transverse motion of the star, and that transverse motion does not exhibit any Doppler effect, because if a source of waves is moving in a purely transverse direction, it does not change with time or with the motion. So there's no redshift or blue shift to be seen. The amount by which the starlight is Doppler shifted is directly proportional to the radial velocity of the star. And so the measurement is quite simple to convert from spectroscopy into velocity in space. And by monitoring the spectrum of the star over a long period of time, corresponding to many orbits of the planet around the star, we can actually attain a very high precision in the detection of its wobble. This shows the schematic, not real data in this case, of the reflex motion of how this Doppler shift manifests. And so here's an example reference to something like an Earth with a one-year motion, and you can see the velocity marked on the vertical axis, time on the horizontal axis. And so this is the reflex motion of a planet orbiting a star converted into a radial velocity, showing its sinusoidal variation of blue shift and then red shift over time. And the amplitude of this radial velocity is a direct, measured by spectroscopy, is a direct indication of the mass of the planet. So a massive planet like a Jupiter will have a correspondingly larger radial velocity. Also, obviously easier to detect than a super-Earth or an Earth. The first exoplanet to be discovered this way was 51 Peg, the first exoplanet of all in 1995. And many of the first few hundred exoplanets were discovered with this technique. As I mentioned, this was very surprising because it was such a fast orbit and such a massive planet. Now in this case, we can actually see the real data that was used. This is not the discovery data, it was a lot poorer and noisier. This is more recent data of that same system, but it shows the sinusoidal variation in radial velocity with a mean of 0. And you can see the error on an individual data point. And with a 4.5-day orbit, if you gather a month's worth of data, you've measured essentially 8 different orbits. So you can imagine this playing out in 2 directions as you gather data. And eventually, you can fold the data over to make one full orbit and add all the data together, all the data points add, and you get a more precise measure of the mass of the star. And that method is used for many of the exoplanets we've found so far. The radial velocity method does have limitations. The most obvious one, as you've seen, is that the amplitude of the radial velocity effect is proportional to the mass of the planet. And at some point, given the errors associated with each measurement, the amplitude will be too small to measure with this method, no matter how much data you gather. Gathering more data is always better and does let you pull objects out of the noise. So bigger planets cause more obvious shifts in the light. Smaller planets cause smaller shifts, red and blue, than the radial velocity curve. And eventually the shift becomes imperceptible. For the radial velocity method, this happens around an Earth mass. And so the radial velocity method is essentially not going to be possible for planets much less than the Earth mass. There's also a fundamental reason for this that's nothing to do with the technique. It's because you're looking at motions induced from the atmosphere of the star. Stars have turbulent motions. We can look at the convective cells of the plasma in the sun, and those cells are rising and falling at roughly a meter or a few meters per second. So what happens as you push down towards Earth-sized radial velocity effects is you start to run into the noise of actual turbulent motions in the atmosphere of a sun-like star, which is a noise effect that you cannot circumvent because it's fundamental to the way stars work. And so it's expected that there's no clever way to circumvent this limitation. And that essentially means we're near the end of the road of what can be done with the radial velocity technique. But it still will be able to pull in masses like the Earth, which is a pretty important benchmark. Another limitation is that the orbital distance, that the gravitational influence decreases over distance. And so when the distance is large, the radial velocity effect becomes small too. And so we can't detect planets of a particular mass at a very large distance. Something I didn't mention is that many of these systems now, many exoplanet systems, have more than one planet. And so the method there allows you to take more than one planet from the same curve. The examples that we've seen are just for one planet orbiting a star. But what if there are several almost equal mass planets orbiting the star? Each of those planets imprints a sinusoidal variation on the star's radial velocity, and they just add together. In mathematical terms, we do a Fourier analysis, and we can pick out each component of those sinusoidal variations and distinguish multiple planets down to the level where the mass is too small, because they simply are additive effects on the spectrum. Now, if there were very many planets, it might get messy and complex, but this technique has been done very well, and it's quite possible to detect multiple planets from a single set of radial velocity observations. And the proof of all this is this amazing curve that we've seen before of how the minimum mass detectable by the radial velocity technique, because these are planets found that way rather than by the Kepler method, has marched downwards. And so this incredible gain in sensitivity over close to a factor of 1,000, or at least several hundred since 51 Peg, is based entirely on spectroscopic precision, on having very accurate wavelength source so that your reference point for zero motion is precise, on having extremely high dispersion spectrographs, so you're dispersing the wavelengths very finely on your charge coupled device or CCD detector and making extremely precise measurements of those absorption lines, and then just having long-term stability of your observational setup, your telescope and your instrument, so that you can gather data for weeks and months with nothing changing. All of these, attention to these details, high precision in the spectrograph and careful experimental technique, are basically the reason why this has happened. There are indeed larger telescopes now than there were in 1995, but much of this work is done without using the world's largest telescopes because the stars involved are fairly bright. Another limitation of the radial velocity method is it tells us nothing about the size of the planet. Because it's measuring a reflex motion and because it's based in the law of gravity, it's about the gravitational influence of the planet on the star and vice versa. And so it's really measuring mass and not size. And there's a redundancy there because a large low density planet and a small high density planet obviously can have the same mass. So the Doppler measurement on its own gives no indication as to how big a planet actually is. It tells us about its orbit and it tells us about its mass, and that's all. Another limitation is the geometry of the system. As you saw earlier, what you actually measure is the mass times the sine of the inclination angle, where the inclination angle is the way the orbit is inclined to the line of sight. In these little cartoons, you can see that in the situation where you're looking in the equatorial plane of the planetary system, you see the full representation of the Doppler shift, of the radial velocity shift periodically. Whereas if the transverse to the line of sight, 90 degrees, you see zero effect, even though this orbit is clearly happening and the star is clearly being tugged in its orbit. Now, on average, you'll be at some intermediate inclination and see some fraction of the full radial velocity effect. That inclination is not measurable by the observation itself, and so that is an uncertainty in the mass that you determine. The reassurance is that once you have statistically large samples and you assume that planetary systems are randomly oriented in 3 dimensions, you can show that on average that underestimates the total masses of an ensemble of exoplanets by a factor of 2. So we've seen that the radial velocity method is extremely powerful. It led to the first detection of an exoplanet in 1995, and it led to the vast majority of the few hundred exoplanets detected in the decade after that. It's based on the reflex motion of a star caused by the gravitational influence of the exoplanet. The periodic Doppler shift in the starlight indicates the mass of the planet. It's a direct application of Newton's law of gravity. Because the shift in starlight is proportional to the mass of the star, the radial velocity can be used to infer the mass of the star. Because the orbit repeats, you can continue gathering data and beat down the noise with repeated observations, and so push this technique right down to about an Earth mass. At that point, it runs into fundamental limitations. The majority of the early discoveries, and still continuing discoveries, are made with the radial velocity technique.